Okay, great. Thank you for still being here with me if you're not too bored of me. And I'm going to talk about the deep learning basics. So I believe everyone has already get AWS credit code and with installation instructions. So that is pretty useful. If you have a laptop, you can try to install for that install instructions. So which I also have it here. It will use Python, Miniconda, and Jupyter Notebook, especially for this lecture and tomorrow's deep learning lectures. So please make sure that you register an AWS account and use that code and increase the limit. So the installation can be uploaded online. You can always access for the slides and follow it one by one in this link to how to install the environment on the AWS instance. And probably it won't work now, but please let me know if either your credit code doesn't work or the installation has some issues. Okay. So these are step-by-step installations. After you following that link, you need to do one more thing to git clone my GitHub for today's all the lecture and all the Jupyter notebooks if you want to run it by yourself. So let's start with the deep learning motivation. So people might ask me why the traditional machine learning models work super good. They have like 99% of accuracy. Why are we still using deep learning? So we should go start from the deep learning history about like 6 or 7 years ago in 2012 when a lab from University of Toronto, Jeffrey Hinton's lab, and they came out this deep learning models which beat the other traditional machine learning models quite a lot in this ImageNet classification. Oh, by the way, if someone don't know the ImageNet classification, it's kind of open classification, start from 2010, and you have about 1.2 million of image in total with 1,000 class, and you try to classify each of the class for what, for example, it's a dog or it's a car, etc. So, as you can see, it started in 2012 with the accuracy. It's around here, low 25%. And then the next year, 2011, it approached 25%. And then you will see 2012, Jeffrey Hinton's lab, their AlexNet result reached to like 60%, 16%. But all the other traditional machine learning models are still above 25%, which is a huge drop and a huge increase in our models' abilities. And then we'll just start to fly. You will see the next year, almost all of the model are below 25%. So everyone is using deep learning, whatever network they're using, with convolution, recurrent. So generate a lot of new innovative models. And you can say in 2017, about like almost all the teams got less of the 5% wrong compared with 7 years ago, which is 25%. It's an amazing improvement. And what can we do with neural network? Besides the image classification, we can also do the object detection and segmentation. So in this image, we can detect whether there is an airplane here, there's probably a small airplane here using the yellow square. And we also can detect there's a person here. You will see there's some small number, and this means how much confidence the model thinks it's a person. So which means here, 99.5, the model I think is 0.5% of confidence. It's a person rather than a bear or something. And so you can go to the Mars RNN which is a pretty interesting paper. And we can also do still transfer. So for original picture, we can add some color it to be a super special painting. We can change different scale based on the other painting to transfer it. Add more shade for the sunset or sunrise, or maybe add more noise to it, etc. So if you're interested, go to the repo to see what is really doing there in the code. Oh, there's another one. Okay. And not only a painting, you can also change a person from a male to a female, from a man to a child. Or if you're using that facial app before, you can predict what you looking like, or will you look like in 30 years. After 30 years, you will be pretty a little bit old, and they will show you what are you going to look like. And so for each of the person here, each row, like the first one is original people, and the later is like the female version, children version, a smiling female version, and male without glasses version, etc. So it's pretty amazing, but the model works a lot. And you might wonder, maybe it's only suitable for computer vision, but research also found like NLP works also good for deep learning neural network. So the NLP group from Stanford University, they're using this kind of model called GLOB, and they train a huge word vectors on it. So for each of the words, they assign to a 300 dimensional vectors. So, and then trying to approximate it, converge it, and in the end, each of the words, either it can be tokenized or already be stemmed, it will be with a 50 value, or if you're trained with 300 dimensions, it will be 300 vectors. And when you do the dimensional reduction for these 300 vectors to, for example, 3D, and you plot them, you will find some really interesting analogies. So on the left-hand side, you will find this male and female parallel analogies with if you connect men and women, which are on each point are being projected to the 3D from this dimensional reduction from its original vectors, you'll find like man and woman will parallel to king and queen, which equals to man minus woman will equals to king minus queen. And it also happened to this word. So for different the verb tense, have walking and walked, it will be parallel to swimming and swam, which is pretty amazing, naturally. Also for the country's capital, for different countries, different capital, almost all of them are parallelized in the 2D dimensions, which is super amazing. But you probably need to do a little bit of trick when you do the PCA for the dimensional reduction. And you can also do machine translation. So for the original machine translation that which Google pretty good at, you transfer some German to English. It will be kind of not that natural language, not natural speaking. It's like no problem can be solved from the same consciousness that they have arisen. I don't really understand it after I say it for the 10th times. But on the right-hand side, when Google using the neural network for language translation, it will be much better. Understand? So you have said problems can never be solved with the same ways of thinking that cause them. It's pretty natural for this language. And a little bit funnier one, which is a recent paper from last year in CCL. It's like you have this content. Can we also do the still transfer on NLP rather than only say we? Yes, you can. So you have this content on 2 dogs playing by a tree, and you want to transfer it to a little bit warm, happy, with love. So you fit them into RNN. It will generate sentence like 2 dogs in love play happily by a tree. And the model will just do that for you. You don't need to create it yourself. we can also combine computer vision and natural language processing to do this question answering problem. So in this left picture, we have a woman with her mustache as a bananas. And you have this question which are in natural language, what's her mustache made for? And then you have two extractor. You have the vision feature extractor, and you have the text feature extractor. So you feed them with like maybe attention models, and you try to pay attention to mustache rather than any other thing, and trying to answer this subordinate object recognition problem. And you combine two model prediction and do the final model training for the predictors, and then the answer will be a banana. A pretty amazing paper last year. Also, more interesting, you can also do the image capturing. So also you have the image and you want to describe what's happening in this image. So the left-hand side, you have all the human label training dataset. So first picture, you have a cutie dog sitting in the heart on the sandy beach. And second one is a cutie dog works next to a little dog on the top of the beach. And third one is a large brown dog next to a small dog look out of the windows, so which are a bunch of dogs. And you want to know when you combine these dogs, you train them, what will happen to the right picture, which you also have two dogs on the beach. And the model is pretty amazing. And they can tell you that a dog is sitting on the beach next to another dog, which is just describe what's happening here by just using the neural network to train. And so here are some problems we're going to trying to solve, and I'm going to demo it using Jupyter Notebooks. The first is definitely classification. To classify different subject, it's like a subset of ImageNet. And second part, we'll do some regression. So you will see different cat. We can not only decide whether it's cat or not, we can also know how much do they weight. So it can be a small cat, it can be a super fat cat. And we can do that using regression, also using deep learning. And we're also going to solve, maybe not today, some sequential problem, or maybe tomorrow when we're talking about recurrent neural network. We're trying to apply the model and let the GPT-2 to generate some interesting article for us. So I will start with NumPy. I believe most of the people here I know it, right? And I will also talk about Deep NumPy, which is NumPy for deep learning. And it is a special package that generates from MXNet. So let's start with it. And these are the n-dimensional arrays. On the ND array are the main data structure for machine learning and neural networks. So everything here are numbers. They are in different dimension of numbers. So we can have this 0 dimension, which is scalar, a 1D dimension vectors, a 2D dimension, which are matrices, and also 3D, 4D, 5D. So example here is like 3D might be a RGB image on which you have this red, green, and blue channels for each of the photos. And the 4D can be a batch of RGB image. So in your photo album, you have different batch of the photos. And you can have the 5D, which is example can be a batch of videos in your cameras or your photo albums. Any problem? Question? And so let's go, after we know the ND data structure, we want to know how to access it. So if we only want to retrieve or extract one element from this matrix, can we do it? So the answer is definitely yes. So we can have this bracket with 1 and comma 2. So it will mean the row 1 and the column 2 to extract this particular element for this matrix with 7. Also, you can extract one specific rows from it which you can have the symbol here. You can also extract a square metric. You can also extract a different values from a same matrix. And that's it for NumPy. The next thing I'm going to calculus is what I'm going to talk about is calculus 101 knowledge. And we're going to start with derivatives. So derivatives is measures the sensitivity of change of the output with the given input. So for example, the slope of tangent is the derivatives. And if you have the function f squared, the derivatives of dx squared of dx will equals to 2x. And so if you have, for example, x equals to 1, then the derivative will be 2 times 1 equals to 2. Pretty simple. And a little bit more straightforward cases, you have those value, y equals to a constant value, then the derivatives will be 0. And y equals to x to the square of n, then the derivatives will be n times x to the square of n minus 1. And for exponential, it's pretty special case. It will equals to itself. And for the log function, it will equals to 1 over x. For sine function, it will equals to cosine. And if y is kind of function, if it's equals to u plus v, then dy dx will be du dx plus dv dx. And if y equals to u times v, then it will equals the derivatives will equals to du dx times v plus dv dx times u. And the final case is the chain rule, which I'm going to introduce a little bit more later. And sometimes you might argue that if my function is not differentiable, what should I do? So you can definitely define the gradient on the no differentiable point. So for example, here you can define the gradient equals to n equals to a, where a is belongs to minus 1 and 1. Another example, if it's a max function, it's not differentiable at x equals 0 either. So we can define this a belongs to 0 and 1, which is the derivatives in the other two cases. So what is gradient? Gradient is kind of another level of version of the derivatives. It measures the multivariable generalization of the derivatives. So both x and y here can be either scalar or vectors, and you can do the same thing at the gradient or derivatives. So be sure that you notice the shape here, since for neural network, we do a lot of matrix calculation. And when you do debugging, you will find this shape is pretty important. And most of the time, you will just calculate the shape yourself. And especially for the last case, you have this delta y delta x have the shape which equals to m and n, where m is coming from the shape of y and n is coming from the shape of x. So how do we get this delta y delta x? What we can do is delta y delta x will equals to delta y1 divided by delta x vector. And for each of the yi, we will do the similar thing in each of the row. And similarly, come to the next step. For each of the column, we'll do the similar thing for xj. So come to the later part, which is .y dot s I and j element will equals to dy element by dj element. Any question? And let's do some exercise. I believe people are tired, so probably we'll just go ahead and give you guys the result. Or if someone wants to volunteer, that would be great. So if y, notice y is a scalar and x is vector, and then the derivatives will always be a vector of shape 1 times n. So for example, if y equals to a and dot y dot x will equals to 0 transpose, And if y equals to AU, then dot y dot x will equals to A times dot U dot x. No, remember this A will be a scalar rather than vector. And if it's a sum, then it will be 1 transport. And if it is x squared, then it will be 2 times x transport. Similarly, if y equals to u plus v, and then the derivatives will be dot u dot x plus dot y dot x. And if it's uv, it will be dot u dot x times v plus dot v dot x times u. And if y is a dot product of uv, then the derivatives will be ut times dot v dot x plus vt times dot u dot x. And pretty straightforward. You don't need to memorize it. It's all available online. And another exercise. But notice that this y here is not a scalar anymore. It's belongs to Rm, which is a vector. So the derivatives will be r m times n with shape of m and n. So the first case will be a zero matrix. Second case will be an identity matrix, and the matrix of A transpose. I don't know what happened here. It's also the chain rule. We're going to talk later. And also here we have if y equals to the matrix A times U, then the derivatives will be the matrix A times dot U dot X. And similar here, it will be A times dot U dot X. Any question? Yes.
Can we please go back to the slide that
Which one? Oh, sorry, I cannot hear you. Oh, n-dimensional?
okay. Yes, another one. Okay, thank you. So I just can't comprehend the idea of 2D vector. What was it actually? So the 1D vector it's just like x, y, and z, right? In the Cartesian space, but what is actually 2D vector?
So 2D will usually call it matrix.
Yes.
So it's like several 1D and Derive, which are vectors stacked together. So it will be 2D.
Is it limit only 3 member for one metric, right? Can it be like 4 member in one metric?
For
2D metric. For 2D.
Yes, it's like 2 by 2 matrix. It can be 4 number.
4 members.
Is that your question?
I just can't picturize what does it look like. So it unable to.
Can you
because the picture that you use a rectangle, right?
Oh, this one or
yes, that one.
This one?
Yes, that one. The one on your right hand side.
Yeah. Oh, okay. So you can think about this way. So think about the example here. In a 0D, we have 1.0, which is a scalar value. And you combine, maybe you stack all the scalar value, maybe 3 scalar value together. It will be a vector, right? And horizontally. And then now, if you want to come to 2D, you stack all the horizontally vector together. So see, there's like 1.0, 2.7, 3.4 in this vector. And we can put them into the first element of the matrix, which is the first row. You can also add more rows here with different elements, and you stack all the vector together vertically, then it will be your matrix. Is that-
okay,
is
got
that
it.
your problem?
Thank you.
Okay. Any other problem? Okay. Let's continue.
Hello. Okay, I just have a question about the derivatives. I don't know if it's
Oh,
true.
okay.
Yeah. I think on slide 50. So there's one that y equals to sum of x, where x is the vector, and the derivative is like the vector of 1 transposed. So I'm not sure why it's that the case.
Okay.
I'm just confused.
Yeah, so first, the shape of this vector will always be r to the 1 of times n. So the shape is always like that. And think about that. If you have sum of x, which equals to sum of x1 until to xn, right? And you get derivatives of it. So for x1, you get derivatives of all the x. You only have the one element for the first one. Yeah.
Okay. Thank you.
Yeah, I think you understand. That's good. Okay, thank you. Okay, let's continue. Okay, chain rule. So why are we talking about chain rule? Because when we do the neural network, we have so many layers. And how do we connect all the layers together? We're using the chain rules to calculate the gradient. So if you have this y equals to fu, and you have u equals to jx, what is the gradient of dot y dot x? So it will equals to dot y dot u times dot u dot x. And this is called the chain rule. And this is applicable for the scala, also applicable for the vectors. You just need to change the scala to the vectors. But also be mind of this shapes, which is originally, if it's 1 times n, then when you do the matrix multiplication, be aware of the shape that the column of the first matrix should be matched the rows for the second matrix. But for the chain rules, think about it. If you multiply this derivatives matrix like 100 times, you probably need to memory too many shifts. You want to code it yourself. And that's why you want to do automatic differentiation using this scientific fancy package like TensorFlow or MXNet. So what do? If you calculate the derivatives by hand, it's hard. Especially if you want to apply this chain rule for those n different derivatives. And if you use computational graph, you can build explicitly using TensorFlow and MXNet, or you can build implicitly using China or PyTorch or Deep NumPy. So what does it mean? So on your right-hand side, it's a computational graph. You have this function, z equals to the dot product of x and w and minus y, which is your target value, and you get the square value of them. So from the below hand side, you have this w and x, which are your input, and you calculate them. For the second part, which is your a, equals to the dot product of x and w, and then you go up one more level, you calculate the b, which are difference between a and y, and then you assign z equals to b squares. So you have this not that complicated computational graph. What it will do, it will go back from z to calculate the gradient, right? And go back one more times to the weight matrix. And computational graph will help you memorize what are each of the elements, what are the corresponding variables. Like for example, for this b, it only need to memorize, like where is this a coming from? What is this value? And where is y coming from? you don't need to take care of both the W and X. And I'm going to show some NumPy in orthograph notebook. I will do that later. If we don't have enough time, I can show tomorrow. Yeah. Okay. That's a good question. Yeah, so the question is, what's the difference between build explicitly and build implicitly? So build implicitly is like pretty straightforward. It's like we have this A plus B equals to, sorry, that's a bad example. We have this 1 plus 1 equals to 2. So which is it's like pretty straightforward math formulas. But explicitly, you will have this 1 plus 1 have 2 cells, like 1 and 1. You have another function called plus, and then you have this computational graph. So you feed your value 1 and 1, and the computational graph will run, and then it will gives you, oh, this is a 2. So that's a kind of difference, especially when we're doing this model package framework, like TensorFlow and MaxData kind of explicitly. So it has built-in computational graph, and which have lots of powerful for the compute. It's much quicker than the implicitly, because when you do implicitly, you don't know what the coming value will be. Will it be a scalar, or will it be a function, or be something, etc. So it will be hard for the model to imagine it, and that's why, so for the package to imagine it, that's why like PyTorch or Chandler kind of slower. Yeah, but that's a good question.
But right now, I think TensorFlow have the eager mode. So is it the explicit graph or implicit graph?
Yeah. That's a good question. TensorFlow do have that in the TF 2.0 or 3.0, I believe. But under that, like wrapper, so the wrapper has that implicitly, but under that wrapper, you will have the like all the computational graph parallel, like putting there, sitting there, and when you have your input on your model that you build yourself, you write your code yourself, and then it just look for you. But when the model digests it to the lower level, it will be the explicit one. Yeah, good question. So for the Jupyter Notebook, I will talk about them in the group later for this class, but you can always access it if you install everything from the link that I have. And we're going to talk about regression now. So regression, pretty simple, straightforward. Any continuous time series data, you can do regression for them. So here's an example. You have this EC2 instance on the AWS. They're sitting there, and you want to know how to estimate their spot price. So we have this G3, which is special machine that you have this 4 means 4x means you have 4 GPU, 8x means you have 8 GPU, etc. And you also have maybe different region and different date. So we want to predict the price based on different time of the spot price on different server that you have, also different region. So can we estimate? It's a pretty simple example. You will do linear models on that, calculate the weights. So we already talked about that before, but now we have different versions. So the basic version, you have all the element scalar value, or you can have the vectorized version, which is the dot product of weight and x plus the bias of weight. Well, the bias is still a scalar. If you want to remove all the scalar, you can have this x replaced by x1, which you add this column here, and you replace the weights with w and b. So you inject this bias as your weights. And so you will remove your scalar, where now the y hat will equals to the dot product of w and x. And L2 loss, similarly, we have 3 versions. So the basic version, pretty simple, straightforward. And the vectorized version with closed form, it will equals to the 1 over n times the square norm of the vector y minus x times w. So it's just for easier calculation in the later case when we do the computation on the neural network. So we have the L2 loss, and we're trying to minimize the training loss. So what we're trying to do is to find the argument mean of the W for the given loss, which is this loss on your right-hand side, which is just derived here. And to minimize some convex function, which will equals to have the derivatives of this convex function equals to 0. And so if we do some using the previous calculus 101 knowledge, you will have this derivatives equal to the formula functions, and you will set up to 0 if W is minimized the total loss function. So the optimal value of W will equals to X transpose times X, it's inverse times X times Y. So it's just calculus here. You just need to kind of manipulate your function a little bit, but you will always reach that as long as your loss function is convex. So the linear model is also a single layer of neural network. You have this input layer with a bunch of features, and you have this output layer with one neuron, and you have this activation function, which is linear function. And you can also stack a multiple layer to get deeper neural networks. I guess I'm missing some. Okay. So I guess I'm missing some value, but let's continue. So you can stack all the multiple layers, get deep neural network, as well as I show you in the previous neural network lectures, the neural network diagram. And this is a linear regression notebook that in Python that you can use neural network, and I will show you guys, demo you guys later. And the next thing is optimization. So we have this gradient descent in 1D. So for example, we have this continuous differentiable function f, which is from R to R. And if we are applying the Taylor approximation, so we can approximate this f of x plus epsilon equals to fx plus epsilon times x prime, which is the derivatives at x, and plus some big O of epsilon squares, which can be neglected if the epsilon is super small. So now we assume that we pick some fixed size of eta that's greater than 0, and we let this epsilon smaller, epsilon equals to minus eta times x at f prime. So why we set up it this way? So in the formula function, if we plug on this new epsilon into the function, it will be equals to fx minus eta times f prime square and plus this big O. So why we want that? So say now if eta is greater than 0, and this value is definitely larger or greater than 0 or equals to the 0. So on the right hand side, this if we neglect this function, if its eta is really small, then the left hand side will be always smaller than this f, which is a function here. That if this derivative is not equals to 0 and does not vanish, we will definitely make some process to approach some minimum. And this means that if we use this x iteratively with this eta times f prime to iterate this x, and we will hope the function fx will decline to its local minimization or global minimization. And if we think about gradient descent not in only one dimension but multiple dimensions, so we can have this weight vector w start from this original w0, and you get a little bit gradient descent to w1 from this circle of w2, etc., but similar to 1D, straightforward. And the gradient direction will indicate the increase in value from the circle from the outside to the inside. And you also have learning rate. So the learning rate will adjust how aggressively you are going to approach to the local minimizer or global minimizer. So if I have a large learning rate, so you will approach your local minimizer pretty quick. But if it's too large, then you will probably diverge. So think of that. If your learning rate is too large, it probably will jump over this W2 to some W3 here. If your learning rate is too large, and if your learning rate is too small, probably one time you'll make a little bit step move every time, and it will take a long time to train. So learning rate is definitely pretty important. Oh yeah, so that's the case. Sorry, I probably took a step. And if it's too small, it takes too long to train. If it's too big, it will just isolate here, like maybe it's hard, and maybe it will diverge. So, so what else we can do for the gradient descent? We can set up for the mini batch SGD, which is stochastic gradient descent. Since if we calculate the gradient, the traditional gradient descent, you're going to calculate the gradient over the total training data set, and you need to memorize it every time. So probably it's too slow. And for some of the data, maybe they're kind of redundant to each other. Like this different kind of line here, they're kind of similar. You don't need a gradient for all of them. And so we can do the mini batch gradient descent. So you choose B example as your mini batch. Usually this B will equals to 32, 64, or 128, and not too big. And for each of the mini batch, you calculate their loss and calculate their gradient. And you will just approximate the total gradient as this mini batch gradient. And so here's a little bit comparison for gradient descent, mini batch gradient descent, and stochastic gradient descent. So for a gradient descent, the batch size for each gradient descent is the total training data set. And for the stochastic gradient descent, the batch size is 1. So it's 1 training examples. It will just update its gradient and update its weights. And for the median batch gradient descent, you will have the batch size of n. As for computation, so the gradient descent is much expensive. It's much more efficient, but it's memory expensive. Since think about that, you're training on the whole training set, and you need to memorize every gradient, and you average them, and that will need a lot of memory. But vice versa, for the stochastic gradient descent, the computation is not that expensive. You just need to compute one example, one gradient at a time. So it's inefficient. Sorry. And for the memory, it has a huge inefficiency. Since one example at a time, you just need to memory only one gradient, right? So the pros and cons here, which are advantages and disadvantages. So you have the parallel processing available for the gradient descent. So for each of the data, you can just parallel them together and get the gradient. And for the mini batch gradient descent, it's a compromise between the gradient descent and stochastic gradient descent. It can inject enough noise, and it won't end up in some saddle points like the gradient descent. So the gradient descent, when you average out the gradient, it probably not be too aggressive or compare with the stochastic gradient descent. So you probably will end up in some saddle points. It's hard to move. So you won't have some super aggressive gradient to move to everything to somewhere else. And for the stochastic gradient descent, it can easily escape from the current saddle point because you will get weird gradient for one specific examples. But it may be very noisy, so you will feel your training graph, training loss like this, super noisy. And next, we are going to talk about softmax regret. Oh, before that, any questions? Yes, please. Yes.
So when you talk about when you derive this algorithm from the Taylor expansion, so at the end, do you actually get the same algorithm as the gradient descent, or is it basically the gradient descent that you get? Okay.
Yes. So this is the intuition for gradient descent.
Okay. So
Exactly.
it's exactly the gradient descent.
Yeah. This is the intuition why we are doing that using gradient descent. Exactly. Maybe I should be clear next time. Any other question? Sure.
Can you go back to the slide, probably the last slide, the gradient 3 gradient stuff? Yeah, this one. So so again, what was the guideline to pick any of these gradient descent?
The dynamics mini batch gradient descent is always the best.
Oh, yeah.
If your data set is logistic, it's like you have enough data, I would suggest mini batch.
Okay. So in general, just take the first one, like gradient descent.
So the gradient descent is like the base case, and it's applied for the total trained data set. But it always being ended up in those like saddle points. It's like your model is hard to generalize because it's always trained on the total data set. It's always like the gradient always being averaged, being normalized. But stochastic gradient descent, you only rely on one specific trained data to get the gradient and to update your weights. So which is not that reliable. It will be too noisy for your weights, right? And that's why you choose a logistic amount of the mini batch size, like 32 and 64, and then you can train that and to think that gradient as your gradient to update your weights. Yes.
Thank you.
Yes. Almost.
I just want to see the gradient descent algorithms. How to choose the step size of the algorithm.
You mean how to choose the mini batch size?
Step size of the algorithm.
You mean the learning rate?
Yeah. Just go back.
This one?
Yeah.
Okay.
This one. No. Yeah. Next one.
Okay.
Yeah.
Oh.
In this iteration, so the step size should be fixed, right? It's eta. I mean eta, the step size algorithm. So, in the practical, how to choose the eta?
That's a good question. So
Yeah.
eta we call it learning rate, as we just said, in deep learning, and so there are a bunch of algorithms that we can artificially choose this, update this eta, so it won't be a fixed value anymore. Like their algorithm state of art will be Adam grad, and also RM's prompt. So different algorithm. I can introduce it to you later or maybe tomorrow if more people are interested into that. And that's like those optimization algorithm that you're trying to update this eta using maybe exponential moving average, like to calculate the gradient and for maybe the past t time step, and you try to update your eta every time based on your current gradient. If it's too large, then probably you will move too far, so you will use that as your denominator and to readjust it. Yeah, so I can definitely talk about it more if we have more time. A good question. And let's go to the softmax regression. So first, what is the difference between regression and classification? The regression estimates a continuous value, classification predict a discrete value, a discrete category. And we have this regression model which will apply some loss function to it, and it will be a single continuous output. And for the multi-class classification, we have this multiple output and one for each class, where multiple loss will be given for each of this output O1 to O3 here. And we want output to reflect some confidence whether we should choose this class or not. So how should we do that? So we can first one hot encode per class. So for this y vector, it will be y1 to yn, and this yi will equals to either 1 or 0. So it will equals to 1 only if this I is belongs to the specific class. And then we train the square laws. We find the largest y hat. However, the max is not differentiable here. So we cannot always do the argument match. We cannot find the gradient using the previously optimization method. And if we use square laws, you will find like if your prediction is 0, 0, 1, and you probably predict some interesting value y hat equals to 0.30 and 7,000. So it's like not in the same scale. So how do we make them to be the same scale? And that's why the softmax regression coming in. You will have this really intermediating functions here. I won't read it, but you can get the intuition for it. So you have the probabilities that you're trying to indicate the conference, and each of the elements here will be the conference for specific class, and all the denominator will be the same. It will be the sum of the exponential to the OI. And each of them will be a number between 0 and 1, and of them will be the probabilities for each of the class, and of them will sum up to 1. So for example, for a given score, you have this, and then when you apply the softmax functions to output your y, will compare with your choose y, then the softmax will be some really smaller value of the same scale, and you can definitely tell that this 0.7 will have higher confidence compared with the other two. And talking about the cross entropy loss. So if we do the cross entropy loss element wisely, which like each y will be either 0 and 1, so you have this minus cross entropy will equals to this function here. And if you have the vectorized cross entropy loss, so you will have this loss of the vector of y and o equals to the log of the sum of exponential of o minus y times o. So each of the y should be, I think it's my bad, it should be between the interval of 0 and 1. So it's any value between 0 and 1. And for the gradient, we can calculate that using this vectorized form, that we can calculate the gradient based on the output for the given loss. It will equals to the exponential of O divided by of the sum of the exponential of OI minus the vector Y. And so don't mix up the regression and the softmax regression, since softmax regression is a classification. I don't know why they talk about regression. But regression we always talk about as linear model, and softmax regression we think is as like K-class classification. And the model will look like this. On the left-hand side, you have the dot product of W and X plus B, which is your bias. And the softmax model will look like softmax of the dot product of WX plus B. And the loss for the regression is square loss, and the loss for the softmax regression is a cross entropy loss. And the notebook, I will talk about drawing a little bit later. So, coming to the real deep learning, MLP, multi-layer perception. So let's first give you guys little bit motivation from neuroscience, which I love. Oh, sorry, there's a question.
There's a scoring.
Exactly. So the output for those probabilities, they are the conference of that specific class.
So if it's really a probability, so if we see like 80%, so can we expect that the 80% of the times the output will be occur, right?
No. So especially that's coming back to the statistical confidence interval. That this it's only like probabilities for that how the model is confident for this predictions. It's not in general. So since this like 0.7 probably will change for the next example. So which means that the model is pretty. It's like the confidence of the model for this example to be in this class is 0.7. So it's not in general case. Yes, good question. And any other question? Yes.
So you said that the softmax regression use cross entropy loss. I'm not sure. Could you is the entropy mentioned here the same meaning as the entropy in the decision tree algorithm, or is it a different kind of formula?
Yeah. That's a good question. And yes, so they're using the same math formula. So you can think them fundamentally same, but the entropy in the random forest, they're like information gains they're trying to calculate, so it's totally different. But they're also using the same thing, the probabilities. So the formula are the same, but you can think them as different terms. When I talk about cross entropy loss, probably we'll use more on this classification models.
Yeah,
Yes.
I'm just confused because in decision tree, I'm trying to fit this notation into the decision tree model where you try to split the data into two sides, into two branch of the tree, and you're saying that you said that the entropy depends on how pure the nodes are, but there is no purity in this model, right?
Yeah. So that's a good question. So in the random forest, you have this information again. Compare your parent and your child node. So you want to know exactly how much information gains in each of the split, right? You want to find the maximum one. And that's why you use the entropy to measure how much noise and how much surprise that this data is giving to you. And similarly here, when you measure this cross entropy loss, it's using the similar entropy formula. It just kind of using some algebraic formulation to reform to this form, but it can be the same, exactly same formula as the entropy. So I would say the previous one is only calculate the difference between different informations entropies, but now we'll calculate a loss. So I believe that's a difference.
Okay, thank you.
But that's a good question. Yeah. So for the neuroscience part of which it's one of my favorite topic, and we have on the left hand side we have the input, and the dendrites is like those synapses that you see here. So they will take this input. It's like your first layer of neuron, and you have this nucleus, which is like your GPU or CPU, which all the computation will happen here. So you have this input, and you have those neurons, and then you output for the cell body. Then you also have this long line of exon, which will transfer the output to the exon terminal. And then the output here, it might decide whether you want to transfer this out if it's a pretty amazing signal, or if it's not, if it's not that big enough. And then this exon will send it to the next layer, and through this exon terminal to the next neuron's dendrite as an input. So that's why the computer scientists got intuition from those neuroscientists, and they trying to approximate or trying to using these neurons structures to get some sense. Okay, so same. We have this linear model has a single layer, and we can stack all the neuron together in one layers to have a single hidden layers neural network. Or we can stack different layers together to make it as a MLP, which is multiple layer neural network, multiple layer perceptron. And we can also go deep and deep to stack more layers. But please remember that don't go really crazy for each hidden layers numbers. So you don't want a bottleneck in the front. Like if you stack every layer together, say you have like output layers with like, for example, 5 unit, then probably your hidden layer should have more than 5 rather than 3. So you want to do some explorations after your hidden layers. So you don't want this bottleneck sitting there, especially in the first few layers. Then that way you will remove lots of features. So you'll lots of information. And then in the later layers, you're trying to condense the size to be smaller. Okay, that's interesting. And so for single hidden layers, you have input X, hidden weights, and bias. So you have the output on W2, B2, and you have this hidden weights, equals to this activation function for the W1 times X plus B1, and you will have this output value equals to W2's transport times the hidden layer and plus the bias. So this sigma here is active function which will take element-wisely for every elements in this vectors. And anyone can tell me why do we need a no linear activation? Any suggestion? There must be people who know it. Okay. So if it's a linear activation function, we can definitely plug this H into this O's calculation. So this O will be X W2's transpose times W1 times X, and plus another B, which was going back to a linear function, which like you can just combine these weights together and it don't really make a difference. And that's why we use no linear activation functions here. So the first and most common activation function, ReLU, rectify linear union. So which is pretty simple. It will equals to max of X and 0. And why we use it a lot? Because first, it's pretty easy to calculate. You have only probably 3 value as derivatives. And second, you probably don't need to care about if X value is a negative value. And the second activation function is called sigmoid activation. So it will map the given features from minus infinity to infinity to a value between 0 and 1. So it is kind of a soft version of this. If you set of like X equals to 1 for all the X bigger than 0, and then you will have a straight line at the 0, and you will have 0 for everything else. So it's kind of not continuous. And what we're doing here is like kind of soft max it a little bit, also sigmoid it a little bit, so to make it a little bit smoother, but still between 0 and 1. And next is hyperbolic tangent activation function. What you're doing is just similar as a sigma, but now you're mapping it to -1 and 1. And this is a function for the hyperbolic tangent. And remember, this hyperbolic tangent activation is pretty useful for only those hidden layers, and didn't say anyone use it in the final layers, because for the final output prediction, we really want it to be within 0 and 1. So it's kind of some probabilities. We don't want it to be negatives, so it's hard to manage anymore. And multi-class classification. So we stack these output layers with multiple outputs from those hidden layers. So it will be the softmax, a similar function as before. We softmax this O1 to OK as the K class. And so here are some hyperparameter tuning you can do here. first is number of layers you want to plug in your network, and second is for each network, how many of the hidden units you want to plug in for each of the layers. As what I said, originally in the first few layers, usually the hidden unit is a little bit larger compared with the input, so it will maybe double the input or maybe choose any other value which is pretty huge, and then you're trying to decrease the unit in the following hidden layers until the output. So you don't want really a bottleneck. For example, you don't want 2 units in this first hidden layer, and that will remove a lot of information. MLP notebook, I believe I can talk about now. So before I'm going to run the Jupyter notebook, any question? Or shall we have a break? Yeah, sure.
So for the ReLU activation function, you have a point at which it's not differentiables, right? So basically you get a neural network that is not differentiables.
Yes.
So what do people usually do with, or
Yeah.
does it have any problem in practice?
Yeah, it happens actually. So it happens, and I believe we already set it to be 0 because naturally it should be 0 because on the left hand side of this x equal to 0, all the gradients are 0. And on the right hand side, if you're still using x as a gradient, so it will be 1, right? But we're set up to be 0. So normally it's not that happening a lot, so we'll just ignore it. Just like think about it as like x smaller. It's like smaller than 0 case. Yeah. Oh, you mean in one neural network? Yeah, definitely. So like especially when you train on the first few layers, we can apply ReLU, and then in the last layer we can apply sigma function, or we can combine this hyperbolic tangents in the previous hidden layer since it will map to -1 and 1, so it won't have some information loose on the negative side. But in the last layer we are still using the sigma. Yeah. Any other question? Okay, sure. Shall we have a break before I run in the Jupyter notebook? Or maybe like, yeah? Shall we have? Okay, if you don't mind, have a break of 10 minutes. That'd be great. Okay, so let's talk about the code a little bit. That what are you trying to do in the real model? How to write it down and put it back to production. So before I talking about all the Jupyter notebook, does anyone like trying to successfully follow this link here on your AWS instance? Does anyone successfully do that already? No? Okay, one. Nice. I say one hand. Should have a special prize for you. Collab. Yeah, you can do it. The two issue. First is like I never use that. If you have question, I don't know how to answer. Second issue is like we already have AWS code, which has sponsored that for each of the students. So you can definitely run it using it, and it will expire if you don't use it, like with this $100. And so if anyone haven't, please do it tonight. It will be super helpful for you if you want to train some models, because the model we're going to talk about today don't have too many layers. You can train your CPU. You can still train it. But the model we're going to talk about tomorrow, it will be pretty complex. And if you're training with your CPU, probably will take weeks. And I don't think anyone wants to do that. So, and please let me know if you found some bug on this page, and I will definitely correct it. So this will probably be your homework tonight. Sorry about that. So let's start with the NDRA Jupyter notebook. So first, we're going to do is we're going to By the way, I want to do some surveys. How many of you used Jupyter before? Nice. Okay, great. So that will save my work a little, much more. So what we're going to do, import some package. Yeah, question. What's that? Oh, okay. So if you haven't used it before, it's pretty simple, pretty straightforward. You can run the code, click this run, like no, I'm click it. So it will consume this function. Thank you so much. It will consume this function. So what does it do?
It's not working on my laptop. I'm sorry.
So you mean this installation?
Yes.
We can figure out this issue later.
Okay, thank you.
Okay. So we can import NumPy and NPX from MXNet. So MXNet is kind of the deep learning calculation package. It's pretty powerful, can do a lot of parallel training, and it's much quicker than the other package. So what is NumPy and NPX? So does anyone use NumPy before? Great. So NumPy is kind of a data structure, and MXNet NumPy is exactly the same as NumPy, but NPX is all the ND array operation that NumPy, the scientific package NumPy, doesn't have. So we call it NPX. So we also need to do the npyx.setup, which will invoke all the experimental NumPy compatible features in MXNet. And next, what we're going to do is create the vectors and query its attribute. So for example, we'll create this ND array, which have 12 elements. And then we can call it .shape, call it .size. And also, we can also construct a 0 vectors with shape of 3 and 4. So 3 rows, 4 columns. And we'll also call mpy.array, which specifically lists what array each of the element value. And we can have this normal function. We can call the np.random.normal, which will initialize normalizely with 0 and 1, where 0 is like the mean and 1 is the standard deviation. Then we can have the size, also 3 and 4. And what's more, we can do the element-wise operation here. So, for example, we have this x, which is array, and we have this y, it's like a 1 like of x times 2. So we can do some plus, minus, times, to the power, so etc. We can also do the matrix multiplication, which times x and y. So notice that we are times the transpose of y because the x shape is 3 by 4 and y shape is also 3 by 4. If we time them, they won't work directly, and so we need the transpose of y. Also, more interesting, we can concatenate 2 vectors together. So for example, for the previous x and y, if we concatenate over x0, which is a row across the row dimension, so here the first part will be the x, and then the second part will be y. So you concatenate over the rows. What's more, you can also concatenate over the columns when you set up this x equals to 1. So this part will be x, and the right part will be y. So concatenate them together to be a big matrix. And more interestingly, if 2 vectors are of different shape, you can broadcast it. So what does broadcast mean? You have this vector A, which is a column vector of 3 by 1. Sorry, row vector of 3 by 1. And you have this B of this column vectors 1 by 2. And you want to do the multiplication A plus B. So what can you do? So the model will automatically broadcast it. So for the A, since it's like a row vector and it only has like 1 column, and then we'll directly duplicate its column to be 2 columns with this similar values. And for B, similarly, it will duplicate this 0 and 1 to new 3 rows, and then both of them will be a 3 by 2 matrix. And then what you're doing is like you plus them together element-wisely. And pretty useful. And next is indexing and slicing. You can access the entire array from different part. You can index it, accessing the rows, accessing different elements, etc. So you can also transform from mx.array to the numpy array. You just need, so for example, if this x is from the mx array, and what you need to do, you just need to take it and think it as a numpy, so it will be automatically transferred back to numpy.array. And another thing, like another direction, if this A is now in this numpy array, then it will automatically transfer back to B, which is belong to mx.array. So you can say when we call the type function, the function A will becomes to numpy array, and the vectors or the variable B will be the mxnet array. So you can transform back and forth. So this is array, and let's going to talk about autograd. So similarly, you need to import the package first. So from mxnet, you need import this autograd function. It's just like a numpy package, np package, and npx. You set up the environment to be comparable, and you initialize this x to be a 4-element vector. So first, if you want to do this auto gradient, probably you want to do is to allocate some space respective to x for the gradient. So you call this function x.attach gradient. So which means you want to get the gradient with respect to s, and you know that for this given value of x, you will have the gradient. So you attach the gradient to have some space pre-stored there. And now you have this function that y equals to 2 times x squared, and you want to calculate the gradient of dy dx. So what are you going to do? So first, you call this autograd.recall function. And within this function, you initialize you define your y, which is based on this function here. And the reason why we want to record is we want to record this computational graph. Because it's like a explicitly computation within mxnet. We define this graph and we record it. We know how does it calculate with each other. And then nothing is happening. When you call y, it will return its value of y. But what is the magic happen is you call this y.backward. So this backward will automatically backward. Remember the computational graph I showed you, those circle? Will automatically backward from the top to the bottom. Oh my god. To the bottom. And so you will get the gradient for x automatically when you call this x.gradient. So for this function, the gradient should be 4x, right? And we do the test x dot gradient minus 4x will equals to all 0, which means they're identical. Anyone has a question? Okay, let's go to the next one. It's a linear regression, which we can implement from scratch using your network. And a little bit different here, we're going to do a little bit of plotting for the model. So we need matplotlib, and we set up it to be displayed inline. Similarly, we import different package. We import this d2l function, and we into the random into the regular like autograd and numpy/numpyx. And we also import this random vector generalization functions. So think about now, we're trying to constructing some labels by randomly generating it. So suppose that we have this true weights, which equals to 2 and minus 0.4. And we have this bias, which equals to 4.2. And what are we going to do? We are going to randomly generate our data. So using this function here, we have this x equals to numpy random follows normal distribution of 0 and 1. And we are calculating this y based on this formula here using the existing w and b, which are initialized here. So what are we doing? We have this true w, true b, and we generated this feature and label ourselves, which is kind of artificial data using this synthetic data functions by this true value of w and true value of b for number of sample with 1,000. So we can check the data set we generated using the detailed plot function that we just imported here. So this is what this function looks like. And it can be plotted within this 2D dimension. And so next function we're going to do is we're going to iterate within the data set, which we call the data iterator function. So you set a number of batch size, which is a mini batch size that you're trying to read one batch by one batch. Usually we set up the value. So now the demo is 10, but usually it's like 32. And then we have the number of sample equals to the length of features. We have the indices, and we randomly shuffle all the indices. So to make sure that all the data we retrieve is random. And now we're going to yield the feature batch by batch. So we have this like batch indices that we just randomly sampling from before random shuffle before and random sample like from the different group. So we yield each features and labels within this batch size for one batch. So for example, if we have the batch size equals to 10, and we call this function data iterator with a given the batch size, the feature, and the labels, and then we can all print it. So we print the x, print the y. So this is the first batch we're going to do, which is like we shuffle the training data set and retrieve the first 10 elements from the training data set. And then the yield function will come to the 10th, the 11th features, and extract the 11th to the 20th feature from the next time of the training. So what we're going to do is randomize initializing model parameters for the W and B, and then we will attach the gradient for them similarly as before. We want to attach the gradient and try to adjust the weight for them. So now let's define the model, which is pretty simple, straightforward linear regression model, which is a numpy dot like x and w, and then we plus this b as bias, and we're using the simple L2 norm as the loss to calculate it, and then the optimization algorithm will be SGD, stochastic gradient descent. And this SGD actually is not the 3-4 SGD, it's a mini batch SGD since we have the batch size here, at least here, and we will use this batch as a training set to calculate the gradient and average it, and coming back to adjust the weight. In this case, why do I use that? So most of the time we will use mini batch SGD. So probably we just use the name SGD here. So probably it should be mini batch KD, I would say. Yeah, so it's a bit confusing. Sorry about that. And yeah, and then we can do the training. We will initialize the learning rate and the number of epochs we're going to train. So the epochs is how many times we're going to iterate through the whole training dataset. So now it's 3, which means the model are going to iterate through the whole training dataset 3 times in total to give us a final model. So within this epochs, we iterate over this batch size of this x and y, and within this autogrid record, we calculate the loss And since we recall the computational graph, we do the L dot backwards, and then we can calculate SGD, which is the weight. And then we will automatically update the weight and go back to the next loop here. So the next data iterator will yield and another batch of the training data and send it back to me with the similar update of the weights. And the other loop we'll just do for each epochs from 1 to 3. And so after we train 3 epochs, it's pretty interesting that our estimate weights, however, is pretty small, and even only after 3 epochs, and with this 1,000 data set. So neural network is pretty amazing, right? Any questions? Okay, it seems that it's too many lines of code here in this notebooks. So let's do it using Gluon for the linear regression. So it's still the similar model, similar case. We initialize like 2W with a exactly same value, and we read the data with this load array functions. And so now we are using some built-in function from Gluon. So Gluon you can think about as a little bit wrapper for MXNet. And it will simplify your lines of code a lot. So previously, if you write MXNet, probably you will use like 10 lines for code, or maybe combined together it's like 20 lines. And now if you're using Gluon, what you're doing to do, you're just from mxnet.gluon import this NN function, which is short for neural network. And you set your neural net, which equals to nn.sequential, which we assume that it will be architecture of multiple layers of neural networks. And for this architecture, you add each of the layers in. So for example, if you want to do the linear models, you can just add one neuron, which is the nn.dense with 1, and you add that to your neural net. And then what you're going to do is that you initialize your weights for all the parameters. No matter how many layers you have, you just only need to call the function once, and it will know that it will initialize with a normal distribution with sigma, which is standard deviation equals to 0.01. And now what you need to do, you just need to define the loss, which are also imported from the built-in Gluon function, the L2 loss. It also have a lot of other loss that we can import too, and I will demo tomorrow more. And the next is we're going to plug everything that we just predefined both to a trainer. And so the Gluon trainer will collect some parameters like those W and those B, and we'll apply this SGD, which is the stochastic gradient descent function, with a learning rate of 0.03. So exactly the same as the previous use case. So when we do the train, we have the epochs in with the similar epochs and similar iterator, and we do the autograd or recall, we backpropagate, we train it, and we calculate the loss. And similarly, it will give us the result. And you might ask why the result is different. It's because that we initialize the weights and bias to be different value, and that's why they are different here. So when you initialize it, you will always see this difference, but it should be pretty minor after a large amount of epochs of training. So any question? Oh, you mean the 0.03 for learning rate? So when we do the learning rate, we usually initialize to be pretty smaller, because if it's learned like step by step really slowly, is fine, as long as we can see some improvement for the accuracy or the loss. But if you put some like really high learning rate here, so probably the model won't learn. It will just diverge. And you don't know whether it's because the data problem or model problem. You just don't see any improvement. It's just like there's no hope for this model. So probably we'll just start with some learning rate like normally in practically it's like 0.005 at the start. and you feel like, oh my god, my model is too slow, so probably can adjust it a little bit better, a little bit greater. But it shouldn't be too small, too big.
So what is like the max that we should not go beyond? Like that?
I guess I never say someone do a learning rate equals to 1, to be honest. I would say 0.5 is still large. Sometimes people do 0.1. I would say this is kind of the maximum I have seen. But you can definitely try it a little bit. But start with pretty smaller learning rate. Yes.
Thank you.
And there's a back question. Yeah.
The first time that I saw people use
Can you
MX.
repeat again?
Why do you use MXNet over PyTorch or TensorFlow? This is the
Yeah.
first time that I
Yeah,
saw.
exactly. That's definitely a good question that people ask. So I will definitely introduce more about MXNet advantages over TensorFlow and PyTorch tomorrow, because fundamentally MXNet is parallel training, so it's like especially training on the backside side, and so it's much faster than PyTorch, because PyTorch you can artificially define like this neuron one by one, and the model doesn't know what is coming now because it doesn't have the computational graph, so it's much faster than PyTorch. Compared with TensorFlow, I haven't used TensorFlow 3.0. I don't know what's happening there. But previously, when I used TensorFlow, it's like super hard to debug, because you have this like computational graph there, and they give you some really weird bug, and you don't know what is really happening within this computational graph. You just know it doesn't work, and it won't return you something. Yeah. Okay, so let's go to. Do we have time? Yeah. So let's go to the next Jupyter notebook. I'm going to introduce a little bit of Fashion MinixNet. So MinixNet, a Fashion MinixNet is kind of a classification dataset. We have a lot of fashion data in it, which are those 10 class of different labels of shirt, pullovers, shoes, or dress, etc. So it's like 10 class. And similarly, what we're going to do, import out the package. And we're trying to download that by calling this download data function. So you will just download it locally, save it to locally from the outside server. So you can check. We have 60,000 of example in the training set, and 10,000 of examples in the text set. Pretty large. And if you call this function, you will visualize the image using getFashionMinixNet.labels function. Each of them will be several pixel, which is like 28 by 28, I remember. And not that high resolution, but still can recognize it's like what kind of clothes. So we can read that using our data loader as before to be the train iterators. And now we have the batch size with 2056. Since we have such a large training set, we cannot use C32 anymore. So so what we're going to do is we're going to have this X and Y generated through this data iterator. So this is kind of a data processing part for the Fashion MinixNet. And what are we going to do with that? We are going to do some classification test using softmax regression. Similar, input those important module, and we're going to load the data by call the DTL dot load data fashion minix function, and with this batch size. So similar as before, we have this like similar function here. And the next thing we're going to do is to initialize all the model parameters. So we have those different ways, and we're going to initialize them using standard normal distribution. Random normal distribution, and also we attach the gradient for the weight and the bias. And by the way, the number of inputs here, we set up the number of inputs feature value equals to 784. When I first see that, I was thinking, what is this case? And then when I recalculated, it's because each image in the fashion mixnet is 28 by 28, and we timed that together, there are 784 pixels in total. And the output class is 10, so we have 10 different clothes. So after we initialize these parameters, we can define the softmax operator that I just talked about. So this is a function for the softmax that you guys see in the previous slides. And what we're going to do, we initialize this x, which will be a random normal function of shape of 2 by 5. And we initialize the x probabilities, well, equals to do the softmax of x, which is apply the previous defined softmax function on this random number here. So we calculate the sum, and it should be 1, because softmax function should always have element add up to 1. So we define the models of the neural net, which equals to the softmax of the numpy dot, this x, and the w, and plus a bias b. So this is our neural network here. And we also define the cross entropy loss, which is the function here. And we define it as a minus of np.log of y hat times the log of y, or times the probability of y. So now we are going to do is trying to classify the accuracy. So we define the accuracy function as a TP and TM divided by all the examples. So similar here. So all the function, as long as they match up to each other, we're going to sum of it and then get average. So this is the evaluation for the accuracy. We're trying to evaluate this matrix of the accuracy over all the examples, and we will call them using the net. It will be the net and text iterator, and so the final accuracy will be 0.08, which is not that good actually. So if we train them on one epoch, then probably it will give us a better result. So we call this function train up epochs on stage 3. You might ask me why it's stage 3, because this will be in the chapter 3. If you go to the book that we have, if we go here, there will be some function called softmax. So you can just go there and find this function from scratch. I believe somewhere here or the next, I believe it's this one, the implementation of it. So because it's chapter 3, that's why we call it stage 3. Pretty stupid name. And so we do define the matrix. We define the updater, which is a stochastic gradient descent, and we iterate through the data iterator, and we do the autograph recording and backward updater. We use this matrix to measure the accuracy, and we do the matrix 0 divided by matrix 2. It's because the matrix 0 or equals to the train loss, and the matrix 2 will equals to the number of examples, and similarly the matrix 1 will equals to the text accuracy, and the matrix 2 also the example. So we want to know the average loss and average accuracy. And next is a whole training function. We combine them together to train. We call it train chapter 3, and similarly chapter 3. So we have the strings and the text accuracy. We initialize them as a list here, and we have this denominator, which is kind of the sum functions, and within the number of epochs, for each of epochs, we call this train epochs chapter 3 function here. So we train them and get the text accuracy, and then we add an animator system using the plotting function. So you'll see for each epoch, we'll point 1 point here, and it will generate the training loss, training accuracy, and text loss here. So you can see as the epochs go larger, the task accuracy will definitely, and train accuracy will go higher, approach to 0.9. Remember, originally it's like 0.08, pretty small, but now after 10 epochs of training, it approached to 0.9. And you will see the loss will always decreasing since the model is trying to update their gradient one more time for their weights and decreasing their loss step by step. And what's more, when you have the model, you can also do the predicting. So you can predict chapter 3. Still, call the data over the test set. And we have this break here because we only want to show a limited amount of pictures. So you can have this choose will equals to detail get fashioned of the true labels, and the predict will be the neural net that here that you just train here when you call this train chapter 3 function. So you'll have the neural net remember all the weights, and it will apply to the new data X that you just called from this text iterator. And then you do the argument max of them to get the predictions. So, for example, since all the prediction will be probabilities, and you want to do the argument max to select which labels do you really want. And then it's a plotting. So the first row I believe is a choose, and the second row is a predict. It seems works pretty well. Besides this, power is a shirt. Actually, I used to think power as a shirt. And for the draft and the code, that's a bad case. Maybe it's not training enough. So that's it for the softmax regression. Any question? Okay, let's go one more to parent book, which is pretty short, pretty simple if we are using the gluon to do the softmax regression. So similarly, you'll call out the package, it loads the data to your train and test dataset. And you define the model with net.n.sequential. You initialize this sequential neural network. So you add one layer. So this layer will be a dense of 10 because you have 10 class to classify. And then you initialize the weights. For each of the neuron, you will initialize with random normal of sigma equals to 0.01. And now it defines the loss function. Similarly, as before, you can just call this softmax cross entropy loss, which will do everything for you. Compared with previously, you need to you need to write the code one by one yourself. So this one line will define the loss, and the trainer, you also just call from gluon and define the trainer with this SGG and learning rate. And you have this DTL.train chapter 3, which I already saved to the detail package that we just described before. And it will give you the similar graph here. So I believe that's it for today. And probably everyone's hungry or want to go to swim in the swimming pool. So everyone have fun, and I will meet you guys tomorrow.